In this video, we will discuss how we can use the fundamental theorem of calculus to evaluate definite integrals. But as a reminder, and to distinguish between the two, an indefinite integral is a family of functions. And recall what that family of functions is. It's all functions whose derivative would be that f of x. And we say it's a family of functions because it typically involves that plus c. Right? We would write the indefinite integral of a function little f of x equals any antiderivative f of x plus c. So it's a family of functions depending upon adding a constant. In contrast, a definite integral is just a number. And recall that that number has a very geometric interpretation. So if we're looking at a function between a and b, and if I kind of just randomly draw the graph, so say this curve is y equals f of x, the thing to note is that there's two enclosed areas that jump out at us. This first area, call it A1, which is enclosed between the curve and above the x-axis. And the second enclosed area, which is enclosed between the curve and the x-axis but below. So in this case, we would say that the definite integral from a to b is equal to a1 minus a2. And the language that we would use is we would call this a net difference of enclosed areas. So note, areas by definition are always positive. We take that area enclosed below the x-axis, and we subtract away that positive area enclosed below. So a1 minus a2. Now to evaluate definite integrals conveniently, we use the fundamental theorem of calculus, technically part 2. So to evaluate the definite integral, what we need to do is find any antiderivative big F evaluated at the upper limit b minus sign evaluated at the lower limit a. So as long as we can find an antiderivative of that integrand, we can evaluate its definite integral. So let's see this in action. So let's start off with the definite integral from 1 to 5 of 3 over x to the 4th. Much like the indefinite integrals we've evaluated, the thing to do is to first write it more conveniently. So 3 times x to the minus 4th. And once we have everything in terms of powers of x, then we are ready to antidifferentiate. So minus 4 plus 1 is minus 3. So we have 3 times 1 over minus 3, x to the minus 3. And the notation that we use is we put a vertical bar, subscripted with a 1, superscripted with a 5. This is telling us we replace every x with a 5, put a minus sign, replace every x with a 1. So I'm going to simplify this just a smidge first. I'm going to write this as minus 1 over x cubed from 5 to 1. So we plug in x equals 5. So that would be minus 1 over 5 cubed, which is 125. We put a minus sign and we plug in 1. So we're subtracting away minus 1 over 1. So what we end up with is 1 minus 1 over 125. And remember what this positive number is telling us, so we could write this as 124 125ths, is it's a net difference of enclosed area. If you were to sketch the graph of this function from 1 to 5, it's sitting entirely above the x-axis, and this is the area enclosed between the graph and the x-axis from 1 to 5. For our next example, we have the definite integral from 0 to 2 of x times 2 plus x to the 5th. And in order to do so, we're just going to, as we've seen previously, do a little bit of algebra. Take that x and distribute it through. So this would be the definite integral from 0 to 2 of 2x plus x to the 6th dx. So we antidifferentiate our integrand. So that would be x squared plus 1/7 x to the 7th. And we're evaluating from 0 to 2. Now a common question that I would be asked is, what about a plus c? Do we need it? And the answer is no, because if we had a plus c, we'd end up with a plus c minus a plus c, and they end up canceling. So including one's not incorrect, it's just simply unnecessary. So we now evaluate at 2. So replace both those x's with 2. So 2 squared plus 1/7 times 2 to the 7th. And we subtract away what we get when we plug in 0. Now note when you plug in 0, you just get 0. So you actually don't even need to write that down. And we have 2 squared plus 128 over 7, which if we simplify that, that would become in kind of a simplified form 156 over 7. Let's now look at a couple more examples. So the first one here dealing with trig functions. So as long as we know an antiderivative of cosine, we can evaluate this definite integral. And hopefully we recall the antiderivative of cosine is sine, and we need to evaluate this thing from pi over 6 to pi over 2. So we first plug in pi over 2, we put a minus sign, we plug in pi over 6. And as mentioned previously, we should know the values of the trig functions at these common angles. So sine of pi over 2 is 1, sine of pi over 6 is 1/2, 1 minus 1/2 is 1/2. So as you practice more, this process should be becoming quicker and more efficient. So one additional example. So anti-differentiating term by term, 2/5 x to the 5th minus x cubed plus 5x from 1 to 0. So we plug in 1, 2/5 minus 1 plus 5. We put a minus sign, we plug in 0. And when you plug in 0, you get back 0. So 2/5 plus 4 would combine together to be the fraction 22 over 5.